First thing I would do is I would find what h is here. Of course, h is going to be just this height. How do we find it? 9 over 12 equals h over 17. Good. So 9 times 17 divided by 12. 12.75. So that's 12.75 feet high. So now for our equations, what do we know about x and y? We know that x plus y is 31 feet. Very good. What else do we know? If I call this A and B, well, I know that 9 over 12, we know that A plus B equals H. You are absolutely correct there. Let's do that. A plus B equals 12.75. But I also know 9 over 12 equals A over X, right? This is X here. So that gives me 12A equals 9X, or 1 1/3 A equals X if we divide by the 9, right? So this X is really 1 1/3 A. Then for Y, we have that 3 over 12 equals B over Y, correct? So we got 12B equals 3Y. Dividing by 3 gives us that 4B equals Y. So this Y is really a 4B. So instead of X plus Y equals 31, we've got 1 1/3 A plus 4B equals 31. I'm going to take this top equation here and I'm going to multiply it by -4. So this is a -4A. This is a -4B. This is going to be a -51. I know I wrote a -BB, -4B, so that should be. So now we're going to do our elimination here. 1 1/3 A plus a -4A is a -2 2/3 A. 4B and -4B cancels out. 31 plus -51 is a -20 there. So now we're going to divide by the -2 2/3. So A is what? 7.5. A equals 7.5. So that means B has to be 5.25. 12.75 minus 7.5. So now I can go back and I can find X. X is 1 1/3 A. So 7.5 times 1 1/3, which is 10. X is 10. Y is 4B. So 4 times 5.25 equals Y. What's 4 times 5.25? 21. And that does add up to 48. Anybody get that on their own? I'm going to have you guys try this one. Give that one a shot. So for this one, we have, of course, x plus y equals 44. We know that 8 over 12 equals h over x, so that 12h equals 8x. Perfect. We divide by 8, 1.5h equals x. So we're going to put 1.5h in here for x. On the other side, we've got 3 over 12 equals h over y. Give us that 12h equals 3y, otherwise known as 4h equals y. So we put 4h in here. So we have 5.5h equals 44. Divide by 5.5. H equals 8. H is 8 feet. X is 1.5 times h, or 1.5 times 8, which is 12 feet. Y is 4 times h, so 4 times 8, which is 32 feet for y. What do you think? Good stuff? If it's a 6, it actually comes out to be a fraction. Add by 4, what do you mean? Okay, so, yeah, by the way, if that was a 6 instead of a 3, that ends up being a 2h, so that ends up being 3.5. 44 divided by 3.5 gives you 12.57142857143. That's h. Yeah. So it's basically like 25 and 19 feet, somewhere there. Okay, well, let's talk about something a little bit different today. I'm going to offer you guys an extra credit opportunity, by the way. In your packet, number 79. Looks something like that. $20 points extra credit for anybody who shows me the correct answers. Now, by correct answers, I mean you must have all 7 of them. J1, J2, Q, H, D, X, and S. Anything's possible for the right price. You must have all 7. But really, if you get a couple of them, the rest of them are going to be easy after that. Also, the first person to show me the correct answers will get 30 points instead of 20. Little motivation to see how fast you can do it. So there's a couple more things we want to talk about. Today, in the first hour here, we want to talk about fascia matches. And fascia matches is actually a pretty important calculation in construction. What fascia matches are dealing with is if we have a roof, let's say this is our house, has a roof on it, and we have a L coming off of that house. Let's say the slope of the L roof is steeper than the slope of the regular roof. Well, of course, your roof comes down, there's an overhang over the wall, then there's a fascia. Well, you want the fascia of the main roof in most cases at least, you want that to match up with the fascia on the L roof. You don't want to have a step up or a step down there, right? So what we're looking at is in this corner here, you have those roofs come together. You want this fascia here to line up with that fascia there. You don't want this to be down lower or something like that. So how do we make that happen? Well, there are two things. There's some constant points here. We have this is the top of the stud wall on one side. Hopefully, that matches the top of the stud wall on the other part of the roof, right? Hopefully our walls are uniform height all the way around the house. If they're not, we can still do this. It just makes life a lot more complicated. So we're going to stick to stud walls that are the same height. So now the truss then sits on top of that. Now, obviously, there's more to it than what I draw. There's actually a bottom cord that comes in, and then the heel height sits up and whatever, and the top cord comes in. We're drawing it kind of a wire frame, so we don't have to deal with all that crap. There is a heel height here, and then, of course, the top cord comes down, and usually the tail ends up going below the height of the wall. In the packet, I drew them so that the tail was above the height of the wall, but that's not terribly realistic. So we have a couple of things here. We have the roof slope for each roof. The slopes are going to be different. We have the heel height for each. And then we have the overhang for each. Now, any of these things can be adjusted. Many times what you'll do is you'll order trusses with slopes with a standard heel on them, or an energy heel actually most likely, and you'll get them on the job site and you'll just cut off the overhang on the truss that's lower so that you cut it back so it's the same height as the others. The problem with that is that gives you a look on the house that some people don't like, where the overhang here is longer than the overhang here. A lot of people like to have those overhangs match all the way around the house. So the most common way, if you're engineering them to match, rather than just doing it on the fly at the job site, is to adjust the heel height. So let's look at an example of this. I'm going to take out my generic here and I'm going to put in actual slopes. Let's say that this is an 8-12 slope here, and this one is going to be a 10-12 slope. And we want both of them to have 16-inch overhangs. So what we are going to do is we are going to have the lower slope truss is going to have a standard energy heel. The standard energy heel on an 8-12 slope is going to be 6 3/8 inches. We've said the top of the wall is consistent, that this height and this height are the same. There's one other thing that is consistent. If the fascias match, this height and this height are the same, right? Those should match up. So what we have to do is we do the math on one truss to get what this height is from that height, and then we make it match on the other one. So over here, if I call this 0, we go up 6 3/8 inches. We need to figure out how far we come down over here. Well, this is 16 inches. How do I find this dimension? 8/12 equals, if I call that x over 16 inches, right? So 8 times 16 divided by 12. 8 times 16 is 128. Divided by 12 is 10 2/3. 10.6667, we're going to call it. Well, what does that mean for our height? Well, how far below this are we? Well, we went up 6 3/8. We have to subtract that 10 2/3. So we're now a negative 4.2917 inches. So from that wall height down to there is 4.2917 inches. Does that make sense? So over here, this has to be 4.2917 inches below that wall height. So now we're going to go up here and back over to get what that height has to be. We're finding this rise here. How do we find that rise? Well, that's 10/12 slope equals, we'll call that y over 16. So 10 times 16 is 160. Divided by 12 is 13 1/3. So this is 13.3333. We're going to add that to the 4.2917. Well, from a negative, I should say, right? That gives us 9.0416. So that means we're 9.0416 inches above here. We have to convert that into inches and 16. So we're going to subtract 9 times 16. So 0.6 was going to round to 1/16. So this is 9 1/16 inches. So we'd order that truss with a heel height of 9 1/16 inch. The overhangs would be the same, both at 16, yes. Does that make sense? What if we want to adjust something other than the overhang or the heel height? What if we're going to adjust the overhang instead of the heel height? Well, what if they want that look? They don't want to spend the extra money to engineer the heel height. It does cost extra to have a non-standard heel height. That's no fun, though. It is, yes. But that's no fun. Let's see what that overhang would have to be. If this one has a 24-inch overhang, let's say this is a 6/12 slope, and we're going to call this one a 10/12 slope. We're going to give this one a standard heel for 10/12, which is going to be 6 and what is 10/12? 11. No, 10/12 is 6 15/16 for an energy heel. 6/12 is 6 3/8 for an energy heel. This overhang. What's that? Yep, we got to start on the one that we know all three for, don't we? So over here, we're at 6 3/8. We're going to draw in this triangle, figure out this drop. That 6/12 equals, call that x over 24. So that's going to be 12 inches, right? So 6 3/8 minus 12 tells us that we are 5 5/8 inches below the top of the wall. So over here, we're starting out 5 5/8 below the top of the wall. So what we have in this one, we don't know the overhang, but we know this total height here has to be 6 15/16. plus 5 5/8. That's going to make that 12 and, what is that, 9/16 inches? So we got 12 and 9/16 inches. So we've got 10 over 12 equals 12 and 9/16 over that overhang. So 12 and 9/16 times 12 divided by 10. We get 15.075 inches. So that is 15 inches. And we subtract the 15. Come on. Times 16 to give us, that is 1.2, so 1/16. So that our overhang is going to be 15 and 1/16 of an inch. What do you think? That one's not bad. As long as if you have two different slopes on a house, it doesn't look horrible if you have all of the surfaces that have a certain slope have one overhang and all the surfaces that have a different slope, the second slope have a different overhang, as long as you match it up that way. Otherwise, it does look weird if you have different overhangs all over the place. Yeah. Yeah, as long as like you have all the surfaces that have a 10-12 slope have a 15 and a 16th overhang, and all the surfaces that have a 6-12 slope have a 24-inch overhang, then it's not such a big deal. Most homeowners prefer this situation where you keep the overhang constant and adjust. What I'm gonna have you guys do in our last 5 minutes of the first hour here. Got number 80, 81, and 82 in your packet. Now for number 81, the overhangs there are 2 foot. You kind of got cut off onto the top of the next page, but those are 2 foot overhangs for both sides on 81. Okay, we'll give you guys a few minutes to work on those. So we're going to look at problems like this. This is a hip roof again, but we're just finding some missing dimensions off of it. So here we're looking for J, which is the length of the common rafter. To find J, we're looking at that common. Let's draw it out here. We have a 36-foot span and a 5/12 slope. We can find H. Now we're not looking for H here, but we're going to have to find it. How do we find H? Equals H over 18 works for me. So H becomes 7.5 feet. What do we do from there? Perfect. Square root of 18 squared plus 7.5 squared gives us J, 19.5. So J here is 19.5 feet. So if it's the same slope, you're right. Z is 19.5 feet. Can we find R? Yeah, this is 18 here, right? So R is going to be the square root of, you got it, 26.538. Which of course can be reduced into feet, inches, and 16ths. I'm going to assume you guys can handle that. How about M and N there? Let me give you that M is 6 feet from the end here. To find M, then what I would do is I would set up a triangle, just like we did with the hip roofs. This is 19.5, this Z, and this is 18 feet here. So that's just that triangle. M, I would set up this triangle. This is M and this is 6, right? So we now have that relationship. 18 is to 6 is 19.5 is to M. Cross multiply and divide. M is 6.5. feet. Make sense so far? How would I find n? The exact same way. The relationship of z to j is equal to the relationship of m to n. Now, since z and j are equal, m and n should be equal here. But if the slopes were different, that relationship holds true. Yeah. Nope, you wouldn't need to do that. If you know z here and j the common, the ratio between z and j is always going to equal, because j can be drawn here so it meets the hip rafter at the peak. The ratio between z and j will always equal the ratio of any two rafters that meet at the same point on that hip. Okay, what I'm going to do is I'm going to give you guys about 18 minutes to work on this packet. You now have the knowledge you need to finish everything in the packet. Now, the packet isn't collected, I will be honest with you, but in 18 minutes, there will be a quiz handed out on the material in the packet. Well, different problems similar to the stuff in the packet.